speak something?
Hello? Hello?
Yes.
Okay, good. All right, folks, I want to discuss LLM for one generalization. So for those uninitiated, I want to explain what this is. So I'm from University of Texas Austin and also NVIDIA. So at these two institutes, we are interested in building generalist robot models. So we take a top-down approach in approaching general purpose robot autonomy. That means that we want to build a generalist approach and then specialize to downstream applications. Like GPT-4, right? So we're trying to build a customized like a language solution for individual application and gradually expand the capability envelope. We want to first build this generalist approach that train on massively diverse tasks so that we can specialize to different language understanding tasks, like become better specialists. So we believe that to build this generalist approach, we need a trinity of three key ingredients. Right? You need powerful algorithms. We need to figure out the data, how do we train the model. In particular, we are interested in the data flywheels, how do we deploy the robot in the wild and then collect data in this kind of never-ending fashion. And the last is like the human node, like form factor, the embodiment. We think like, so for building robots and the embodiment largely determines what you can do, right? So if you work on robot dogs, at most it's dog level intelligence. If you work on tabletop robot arms, at most, the kind of sensor stimuli, the robot access will limit it in the workspace, right? So that's why we've been kind of putting a lot of emphasis on this emerging new platforms like humanoid robots. Here, this GTC video that we announced like in the last March. This is actually a lab so based in Santa Clara, called the Gear Lab that I'm co-leading with my colleague Jim Fan. We're working with a limited number of like humanoid robot companies building the AI solutions and for this kind of human-like form factor. So if you think about how do we build this kind of a general purpose autonomy for this kind of a humanoid robots, right? So I think we can draw a lot of inspiration from human intelligence because we are the one who made it at least once, right? So and particular framework that I really like to think about this is like basically characterized by this book, Thinking Slow and Fast and Slow, by the Nobel Prize winner Daniel Kahneman, who unfortunately passed away earlier this year, where he characterizes two modes of thinking, right? So the system 1 and system 2. So the difference between these two is system 1 is a fast, intuitive, and sort of emotional, unconscious. It does it like instantaneous without too much thinking, deliberate thinking. System 2 is like a high-level reasoning and deliberate thinking and planning to make high-level decisions, right? So I argue that if we want to build an autonomy stack for general purpose robot, we need to effectively integrate this two mode of thinking, right? So you need to do high-level reasoning on plan. What are the sub-tasks you need to do to achieve a certain goal? And also not just what to do, but also how to do it, right? So like actually in the sensor motor space, determine what kind of actions and actuations you need to take in order to fulfill the goal with a skillful manner. So if we look at the space of recent innovations of large language model, vision language model, I argue that we made a tremendous progress in the system 2 layer on the high-level planning and the reasoning, right? So especially using the tools and the VLMNM, this is the fantastic work done by my colleagues and friends in the community, right? They have demonstrated that if we have a powerful large language model or foundation model, you can leverage this as the system 2 model to do reasoning planning and in the form of a code or in the form of natural language and to scaffold the long-term manipulation or mobile manipulation tasks, right? And the work on CPAN, Qualcomm, and the police policy demonstrate that if you have a set of like action library that effectively abstract away the low-level control problem, so that if you can operate on the high-level action abstraction with action primitives, and you can actually generalize very effectively on the high level. In fact, earlier this week, and probably you see like an announcement from OpenAI, GPT-4o or Gemini from Google, that they demonstrate a very impressive real-time response like demos, right? So that you can turn your camera on your mobile phone and pan around and ask questions that get response in real time. So you can imagine now we're not having a camera, but it's like the robot's eye, they look around. And integrating this kind of VLM tools, it can immediately give you that kind of high-level scene understanding and pursue like a high-level common sense like required for robotic like a long-term manipulation. But One missing piece is the low-level dexterity, which is really one of the fundamental problems in robotics, right? If you, at the end of the day, you want to deploy robots in dynamic, unstructured environments, it's not about just what you do, but actually how to actually operate in this real-world environment. That often require the robot to perform like precise and dynamic skills. This kind of skills and precise what kind of reinforcement learning method or deep reinforcement learning are particularly good at. Here are the 4 demos that I'm showing you, like robots performing very agile and dynamic behaviors in unstructured world. And that's largely enabled by deep reinforcement learning as a very generic learning algorithm to be able to learn policy from this kind of data-driven approach. But often, one important caveat of this line of work is it requires meticulously designed reward function for this to learn the desired behavior. If you look at the papers, right, so from this work correspondingly, these are the reward functions like so mentioned in those papers, right? As you can see that they are quite complex and not intuitive. Often there's many nodes to tune, right? So many hyperparameters, and it requires a lot of domain expertise and for the human researchers and to actually come to tune the norms and so that we can kind of gradually shape the robot's behavior towards the desired one. So deep reinforcement learning works for building the system one, but the catch is that it requires a complex and human engineered reward function. So that really inspires us to think, so how do we actually achieve systematic generalization for system one? So is there any role that this VLM LLM can play in kind of building the system one model as well, given success in system two? So this is like the fundamental problem we are aiming to address in a recent work called Eureka, right? So it's a universal reward design algorithm through some kind of evolutionary search powered by large language models. It's a single pipeline that can unlock like these dexterous skills, as you can see here, the pin spinning, and also a variety of robotic behaviors that outperforms human written reward functions and a diverse set of robots and tasks. In particular, we want this 3 key characteristics, right? So it can do open-ended improvement. It's not just kind of tuning a few numbers in the reward function, but actually kind of make bigger changes and edits on the rewards. It can generalize broadly to a variety of behavior rather than focusing on a few of them. And also it can achieve this like highly agile and dynamic behaviors. So the first work is called Eureka, where the key idea is that to have LLM propose and write reward function candidates and evolve progressively to improve them. And all happens in the context of a large language model. So here, the idea is quite simple, right? So we first like describe the task we want to do in natural language as like English sentence. See, I want to do the pin spinning to a target orientation. And we already have the simulation implemented. That's the source code that you can implement in ASIC or Joko, whatever the simulator you like. And then we are using the LLM's capability to understand natural language and the code together, and put this at the context of the LLM to generate reward candidates, right? So based on the kind of task you want to do, you propose some reward candidate in the form of code. So the key idea is that extracting policy or behavior directly from LLM is hard, right? So LLM is not like serving as a trajectory generator, but it's pretty good judge in kind of telling us whether a particular behavior satisfies the conditions like as we specify by the task specification. Okay, with this type of like high-level approach, you can generate one reward function, but often if you do that one shot, it's usually buggy and suboptimal. So the way we do it is just generate a bunch of them, right? So hopefully, like a subset, if not all, of this reward function can run is bug-free that allows us to kick in the kind of evolutionary loop. So we generate a bunch of candidates. The way we do that is by feeding that into a deep reinforcement learner. Here, this is the expensive part because like on the higher level, we are doing the evolutionary research of the reward function, and then there was reinforcement learning in the inner loop, right? So we really want to make the reinforcement learning run fast so that we can do the iterations in a fast manner. So this is enabled by the GPU accelerated simulation done by NVIDIA that we can parallelize the training with thousands of copies of robots on GPU so that you can actually get this pin spinning policy in 15 minutes, 30 minutes time, right? So this is super fast if you have a very beefy GPU once you have the reward function. that allows us to quickly iterate and get feedback from the training group. So the training gives us some kind of feedback in the form of task success, as like whether you did the task or not. And then we use that as a supervisory signal to back to the LLM to improve the real function design. If you think about so how human engineers and design the reward function based on that feedback. And what we do is like we open up like 1DB or like TensorBoard and we look at the training curve, okay, and then see how actually the reinforcement learners make progress in maximizing the task reward. And then by looking at this plot, we kind of come back to fix here and there. The thing is like for LLM, at least now this current version doesn't reach tasks. So we need to find a way to stringify this kind of information so that it can consume. So the way we do that is basically like put that in an array with numbers where the like specific number means like the reward you achieve at a different number of epochs. But the issue is that if we're looking at like the raw numbers, 0.3, 0.5, it doesn't really mean much, right? Because we don't really know why this reward is good or bad. So we need to give a little bit more information. So the insight that we have is that if you look at the human engineered reward function, how it's like if you really follow a certain structure, it has like several subcomponents and you add them up with some kind of weighted sum. And that kind of an individual component will have more semantic meanings of what this is like real function is doing. Some are kind of penalizing some bad behavior, some are encouraging the robots to reach a certain goal with some distance metric. So by looking at this kind of a reward component, it's basically breaking down that the total reward function into pieces. That gave us like a more informative signal. Like, so how is this reward function doing in shaping the robot behavior in a particular way, right? Either this is like rotation or distance. And by breaking this down the reward this way, we see that well, the rotation of reward is improving because it's actually trying to align the path towards that configuration, but the distance reward is a bit like it does not really change much, right? So using that kind of breaking down, and then the LLM can have a more targeted change of the reward functions based on that kind of information. So our LLM can come back and to modify the reward function based on that kind of environment feedback. It can change numbers in that kind of hyperparameter, but this can be done by a more classical like Bayesian optimization algorithm. But what's cool about it is that it can also make a more aggressive change in the reward function design. For example, you can kind of change the form of the functions, like change the way how we calculate the distance. And also add new components, like if you figure out you need some additional regularization term or penalty term to shape the behavior, the LLM can do that by adding new reward components. So that's it. And then if you put them together, that's the whole Eureka algorithm, right? So they use LLM to propose reward functions, but it's not going to be perfect from one shot. And like the way we validate and examine the quality of reward function is by putting the reinforcement learning in the loop that's powered by large-scale fast GPU training. And then we do this kind of iterative feedback to gradually refine the reward function towards what we want to see. And that's basically what allows us to develop this kind of generalized for reward function designers allows like system one generalization. And what evaluated this on a bunch of robotic tasks I'm showing here, and the main baseline is a human engineered reward that really kind of requires a lot of domain expertise. You need to know how the simulator works, what's the ASIC or all Majoko APIs, and so you need to look at a lot of trial and errors and the know-hows and to actually kind of craft the right type of architecture. We see that for Eureka, that the first round of iteration is actually underperforming the human reward design. That's like the red dash line. But over the course of like progressive refinement, evolutionary research, and you see that the performance gradually increase, and so that if you towards like the end of the fifth iteration, we already like so outperform the human design reward. And also we show that this kind of iterative evolutionary research is important. If we just kind of like the LLM to propose a bunch of reward function in the first iteration, that's essentially the green line, right? So this kind of iterative feedback from the environment which are in the loop is critical for the like LLM to be able to find a good reward design. So the upshot for this work is that Eureka can perform automated reward design to learn the system one level dexterity while not specializing in the one task or one behavior, but it's actually capable of learning a variety of behavior within the same algorithm, right? So here I'm showing you different type of pin spinning with the hand up, hand down, like different orientations, like using the same method, the entire framework without any kind of tuning of a hyperparameter, it was able to generalize to all this different variety of hand spinning, like dexterous manipulation behaviors. So we show that this type of the idea is like rather than extracting the system one dexterity directly from LLM, so we can use that as judge in the form of reward functions to provide signals for system one learning. But there's a catch here, is that everything that I'm showing you is simulation, right? So at the day one robotics, we want to take them in the real world, and like this is only possible because we have such a beefy simulator that you can parallelize and run. But we haven't really showed the utility of this in the physical hardware. So that leads us to the second work called Dr. Eureka. Now, like a Eureka graduated from elementary school to become a doctor. And that we actually put that on the physical robots in this case. This is enabled by aggressive domain randomizations in kind of large-scale simulation environment. And here I'm showing you the robot is trained in ASAC simulation on this kind of U-level kind of walking task. Simulating the U-level is incredibly hard, right? So because like a lot of the simulation to be able to run fast is rigid body simulated. You don't really simulate that kind of deformations very well. But through like aggressive domain randomization, training the robots on a variety of different conditions, you can actually kind of transfer that zero shot to a real world setting where the U-gas ball is kind of bouncy and deform all the time. So this is a gallery of quadruped U-level walking policy purely trained by Dr. Eureka in simulation and transfer to the real world. And Will is the leading author this year, brave enough to put this robot on Philly's like straight and they've been walking the dog all the time. So compared to Eureka, right? So we found that to take the robot to the real world, safety is really important. Like in simulation, all you need is to specify what the robot wants to do, and just that's it. But to be able to transfer, you need to add additional kind of specifications, right? So now you need to tell the LLM that is running on a level, so don't fall off, and because it's kind of dangerous. So based on that, and it will propose additional components to regularize the behavior so that it's like safer than like only in simulation. We found that kind of the additional safety specification is important for the policy to transfer. If without the safety terms, and the quadruped is gonna walk anyway in simulation, but only with the safety term that the quadruped is gonna be able to walk properly in the real world. So we run the Eureka loop to get the initial reward function just like our required work. And now the way we do it, we need to kind of tune that kind of domain randomization terms for it to be able to transfer zero shot to the real world. So we need some kind of environment feedback from the simulation. The way we do that is by rolling out the policy in kind of different like, physical conditions with like different range of physical parameters from gravity to mass to frictions. And you just kind of get a sense of like a quantitative how the policy is going to perform under different physical conditions. And we use that as the kind of a signal for the LLM to tune that kind of physical parameter range so that like the policy can be learned properly in that kind of range of physical parameters and also transferred to the physical world. Because if you train always on the full range, and then the policy is incredibly hard to train, and also sometimes it learns a very conservative behavior. It just learns to not move at all because doing anything will lead to failure. Right, so tuning the right kind of physical range will be important for learning good policy and also transfer to the real world. So this is kind of like the raw output from Dr. Eureka for the randomization generalization, which see that the nice thing about using LLM is not only it generates a parameter, it also generates explanation in natural language. So there was some interpretability by design that tells you why it tuned this like a physical range in this way or one way or another. And then we train this final policy on this kind of in simulation environment with the normalization as specified by that kind of range, and then transfer to the real world. So this is the entire Dr. Eureka loop. Okay, just to show you here, these are some additional examples of ball bouncing. You can also show this works on deflating ball. And all the codes and are online for you to try out, and including the simulation environment. So I'm kind of running out of time. So just one last thing, just like David, we have one more thing. Like so far, I'm showing you designing reward function given the environment code, right? So if you think about the entire MDP, there's a state, there's actions, there's a dynamic, there's a rewards. And so far, we only focus on one piece of the puzzle. That is only given the environment, design the reward function. But in the future, what I'm moving towards the generative simulation to be able to incorporate the generative AI tools, both large language model, like text to video, 3D model, to be able to generate the full-fledged physical simulation for robot learning. I think that's where the future is moving. So just like give you a sneak peek of like what we have been doing in this space. And these are the kind of bunch of gamification environments that we use large language model as a source to prompt and then generate a bunch of like different kitchen layouts and with robot, like mobile manipulators that do different things. And it has cross-embodied support. Humanoid is one of the key platforms, and we also support Humanoid alongside with other wheeled mobile manipulators. And we use 3D generating tools to generate the assets and that we can import in the physical simulation. Really, the cool thing is like similar to Eureka type of approach, given the activity, given a list of like a skill library that robot can do, we let it propose kind of a natural task in kind of a human-centered environment. So what would the human do in this case? Because the large language model are trained on human-centered data, right? So it captures kind of ecological statistics of real world. What would humans do in their everyday, day-to-day activities? By doing this, we can get a bunch of the natural tasks that follows kind of the natural distributions, and then we can design the simulation task that way that it follows kind of a natural distribution of human activity that we care about for training. And not only we have the simulation environment, we also have like a data engine that be able to generate a variety of different behaviors in this like for training. And this is a new effort called Robot Casa, and that's actually an RSS paper that recently got accepted. And we are going to open source everything with MIT license, with all the assets, libraries, and tools, and including the data set simulation, and also human demonstrations, everything on Monday. You can visit that robotcasa.ai. The website is on, but the link will be live on Monday. All right. So, and the final vision is that I show simulation, I show real data, right? So, to build this kind of humanoid robot foundation model that we have been focusing on, we really believe that data pyramid, that we need a large scale like a web data where we train the system to model, like that's going to be a VLM, LLM, and we use simulation data to generate tons of experiences that together combined with a small amount of real world data to build a system one, system two integration. And that's where we're going, and our NVIDIA team is current. So feel free to talk to me if you're interested. Thank you.